All right, so we're moving into our next body system, which is the cardiovascular system. And we think about cardiovascular, we're thinking cardio, which is the heart, and vascular, which are the vessels, So the heart is the pump, and the vessels are the pipes. So what it's pumping and piping is the blood. So we're going to first talk about blood. That's the essential stuff of the cardiovascular system, because if we don't have oxygen and nutrients in the blood feeding the tissues, the body dies very quickly. So we need that pump, and we need open vessels, right, to feed all the cells of the body. So we're going to talk about blood. It's a connective tissue. So it's the only tissue in the body that flows throughout the body, because most of our connective tissues are stuck in their particular system, right? Like the skeletal system, bones are a connective tissue, fat's a connective tissue. It doesn't move around the body, but blood does. It's the only tissue that flows. And the plasma is the matrix. Remember we talked about all connective tissues have a matrix, which is like the soup, and then it has a solid piece, which are the cells. So plasma is the matrix of this connective tissue, and the red and white blood cells and platelets are the cells, and that's what we called in lab the formed elements, right? So we're going to talk about all the unique chemical reactions that occur as a result of the components of blood. So when you look at the functions overall, it's all about transport. It's delivery. It's delivering oxygen, nutrients to cells, and picking up waste and getting rid of them. So gases, nutrients, waste products, processed molecules, regulatory molecules. Hormones are really good for that as regulatory molecules. So we find a lot of hormones. Processed molecules from digestion or from other cells that produce things from the digested products, like when we make hemoglobin, for example, or we make a protein, like an antibody, that's transported by the blood. Regulating pH and osmosis. So our blood, if it's really concentrated, it's going to pull water by osmosis, because water always flows from a dilute, where there's more water, to where there's more concentrated solution. So if we have a lot of salt and sugar or proteins, plasma proteins in our blood, that pulls water in by osmosis. And what do you think happens to blood pressure? It goes up, because when you pull water into blood vessels, that's more fluid in the piping system. And then what does the heart have to do? The heart has to work harder, right, to pump all that extra fluid. So that's why we tell people that have heart failure to not drink a lot of salt, or not eat a lot of salt, or drink salty beverages. Like diet soda is high in salt. So soups are high in salt. So we try to, limit that. pH, our pH of blood should be what number? Do you remember that number from the beginning of the semester? Yeah, very good. 7.35 to 7.45. That's an important number to remember. It's slightly what? Acidic or basic? Slightly basic, right? But if we drop anything below 7.35, clinically we call that acidosis, because that's on the acidic side for what blood should be, even though it's still above 7. Maintaining body temperature. That blood is warm. We find that arteries and veins, the major ones, lie right next to each other. And we're going to see that in lab. Those arteries and veins lie right next to one another to share that core body temperature. And the largest of veins and arteries are found in our core, running right down our midline. So that maintains our body temperature. And what happens when it's cold outside? What are the first things to get really cold? Your hands and feet, right? Or fingertips and toes and your nose, right? The extremities have the smallest blood vessels, so they are the ones that are going to lose that heat. Exactly. And in the dying process, the body shunts that off. So the core, blood is always directed to the core to keep the main organs alive when we're freezing to death, heaven forbid, or dying. So we start to see, bed sores develop in people on their heels, right, when people are dying. So in the healthcare system, sometimes we're a little judgmental when we see a elderly patient come in from a nursing home and their heels are worn down to, stage 4 pressure ulcers. Or their sacrum, right, where the skin is really thin there. And that's not always a reflection on poor care. It's a reflection on an old and dying body, that the blood supply is shunted to the brain, heart, and kidneys, and the skin is a low priority, right? So then if the skin isn't getting proper blood supply, it breaks down, right? So be cognizant of that it's not a reflection on the care all the time. Now it is sometimes, definitely, but in a person, an old, elderly, thin person who's not eating and actively dying, their skin is going to break down, and that's just going to be, you know, part of the process of dying. Protection against foreign substances. What do we have in our blood that protects us from foreign invaders, like the influenza virus? White blood cells, and what do lymphocytes produce? B cells and T cells. They produce, like, why do you get your vaccine? Against all these, yeah, antibodies. Our body produces antibodies, our lymphocytes produce antibodies that are soldiers on the front lines ready for when that infectious agent comes into our system, bam, it's destroyed and killed. But now if you don't have the antibodies because you haven't been exposed or you haven't had your flu shot, then it takes your body about 2 weeks to make the antibodies and to annihilate the virus or bacteria. So then people are sick during the time that their body is making antibodies. And for some people with weakened immune system, they'll never make the antibodies and they're going to die of symptoms related to that infection. And again, that's why we get our flu shot, to protect us. Yeah, great. But number one, if you're going into a healthcare environment and working with people with poor immune systems, you're protecting them by not bringing that virus to their bedside. And then clot formation. We have factors in our plasma that are clotting factors. They're dissolved in the plasma. And people that are hemophiliacs, they lack those clotting factors and they have to inject themselves with the clotting factor when they cut themselves to make sure that they get the ability to stop bleeding like the rest of us take for granted. And then we have the platelets too that start the process, and those are just floating around in the plasma and they plug the hole of the capillaries when there's bleeding occurring. So when you look at the composition of blood, we looked at some of this in lab. More than half of our blood, if we spin it down in a centrifuge, the heavy stuff, the solid particles settle to the bottom. That's the formed elements, and that's red blood cells and white blood cells in that buffy coat. And then the rest is this yellow liquid called plasma. If I look at the plasma, this component, it's mostly water, 91% water. And where does that water come from? Do we make water in our bodies? Nope. We drink it and eat it. Yeah. So if your patient is not eating or drinking, we better be giving them some IV fluids, right? Or tube feeding to make sure that they're getting some fluid in their system. And people, especially with people that have, you know, urinary problems, they forget to drink. Because if we need them to pee and avoid having to straight cath them, then they need to drink, right? Because we don't make we make a little bit of water in metabolism, but because remember that's one of the byproducts of metabolism is water vapor, but not enough to keep things going. We need it in our digestive tract. So if I have high blood pressure, do I want to limit the amount of fluid I'm drinking in? Yeah. Yep. Or heart failure. Definitely with heart failure you need to watch it because the heart can't pump all that extra fluid. So the other, 9% is protein. So there's a lot of proteins in our plasma. Albumin is a really important protein. It's a carrier protein and it also contributes to our blood pressure. If we have low albumin, that's going to prevent that osmosis to keep our blood pressure up. So if there's no solute to draw water in by osmosis, water stays out in the tissues and blood pressure drops. And if there's a bunch of water in the tissues from low albumin, what does that look like? What does my patient look like? Puffy. Yeah. What do we call that? Edema, right? So puffy legs, and it goes with gravity, right? So people have really big legs and big feet. Puffy, where you push it and it's like, you know what the kids play with those squishies, right? You push a squishy and it slowly comes back up. That's called pitting edema in people that have a lot of fluid in the tissues, and that's really nasty for them because that can impair blood flow. It can cause breaks in the skin, and the fluid will actually bubble up and form water blisters on the surface of the skin, and then they'll break, and they'll be continuously losing fluid through their tissues. I mean, we've had people that we wrap towels around their legs, and we're changing the towels every hour because they're soaked with fluid, and it's plasma. It's plasma that's leaking. If it can't go through the kidneys into the bladder and be urinated away, it rises to the surface and comes out of the skin. So when you see water blisters on people, you need to let someone know this person is not getting rid of fluid like they need to, and they need some thing to kick in their kidneys, and that's when we give them medicines to turn on the kidneys and make them pee a lot. Okay, so we have all these proteins in there. Globulins are antibodies. So when we talk about globulins, those are the antibodies that you formed from exposure to foreign materials. And then fibrinogen, I mean, if you look at the percentage here, most of our plasma is water. We already talked about that, but the rest, proteins and antibodies. Antibodies are proteins, so these are just, this is a special type of protein, albumin. Carrier proteins, again, causing water to draw in. These are large proteins. Globulins are antibodies. They're smaller, but they've been formed by your immune system. And then a really small percent of our plasma is this fibrinogen, and this is for forming clots. And we need to form clots. This is a very, very important protein, because if we cut ourselves and can't clot, you will bleed out very quickly, and that's what happens to hemophiliacs and people that are on blood thinners. We interfere with the clotting process in people that are at risk for heart attack and stroke. So when people have a lot of narrowing of the arteries, arteriosclerosis, we'll put them on a blood thinner. Or if they get an artificial valve or a stent, we'll put them on blood thinners, because those are foreign things that can cause blood to clot around those foreign objects. And when people have heart arrhythmias like atrial fibrillation, when the atria are just quivering and they're not pumping fully, when blood pools and sits, it clots. So those people need blood thinners. So we have to interfere with that fibrinogen and not let it do its job fully, otherwise people will die of a heart attack or stroke. And then the other little bit, so that's 7%, the other 2% of the 9% that's not water are ions that we're bringing in from the outside, nutrients like carbohydrates, fats, proteins, waste products as a result of metabolism, gases, carbon dioxide and oxygen are the only gases we care about and can use. And then regulatory substances that are, again, hormones are a good example of that. So we talked about in lab already the platelets, the red blood cells, and the white blood cells that form the formed elements. You can see that the most numerous are the neutrophils and the least numerous are the basophils. And the rest are these red blood cells. So when you look at blood, makes up about 8% of our total body weight. That's a lot. 1.5 gallons in men. That's a lot of blood. That can be lost very quickly if you cut an artery. So we have to look when we see, blood that's spurting in bursts, that's cutting out of an artery, and how do we stop that? Tourniquet, yeah. Above where the spewing is, right? So you take a t-shirt off and tie it really tight right above that site. Okay, so we talked about that. Now serum is a word where we take plasma and get rid of the clotting factors. So if someone gets bitten by a snake and a rattlesnake, the toxin in that rattlesnake saliva can kill a person. So they run to the doctor and they get what's called the anti-serum. Anti-serum is plasma without any fibrinogen, because we don't want to add extra clotting factors to someone who got bit by a snake. We just want to give them the antibodies that someone else has formed from that rattlesnake exposure. So we give them the anti-serum. So it's just plasma without fibrinogen with the antibodies for rattlesnake venom. And that's how the healthcare workers that were taking care of people that had Ebola, remember that years ago? When the big scare of Ebola. Well, once they were exposed, they instantly were given the antibodies. So if I give someone the antibodies to a disease, that attacks the virus right away and then they don't have to get sick, right? But if I just let someone make their own antibodies, they could die in the process related to the symptoms of that disease. So same thing with tetanus. If you cut yourself, and expose yourself to tetanus, they're going to give you a tetanus shot, but if they think there's a real exposure, they can give you antibodies, the anti-serum to that. Same thing with like the black widow spider and all those things we know that you need antibodies for. Rabies is another one, right? You get bit by a rabid dog, they're going to give you the antibodies and not wait around and let you form your own and become rabid in the meantime. So that's what serum is. Okay, so we talked about plasma, And we donate our plasma for people that have bleeding disorders because we're giving them what? Yeah, the fibrinogen. And there's other clotting factors that are even smaller that are related, and we're going to talk about that. People that have lost a lot of blood from trauma, they need the plasma to boost up their blood volume. People that are in shock, they need all those products, and again, in the plasma to recover, because they're not going to have those conditions, or they're not going to have those components that are critical, like the ions and the nutrients and all that. Live conditions, what? What? I don't know what that. Oh, liver, thank you. I didn't even know my own notes. Yeah, I haven't looked at this in a while. Liver conditions, yes. Because the liver, thank you, makes these proteins. So these, other than the globulins, the albumin and fibrinogen is made by the liver. So if your liver is shot with, what is the number one cause of shot liver in our patients? Alcoholism, yeah. Lifelong alcoholism, or hepatitis from IV drug use, or hepatitis from exposure in a restaurant that was never treated. So we do see liver disease from that. Well, they can't produce albumin or fibrinogen, so they're going to be all full of edema. Again, osmosis can't pull in water if the albumin levels are low, and they can't clot, so they're going to bleed a lot and have big fluid on board, especially around the midsection. Okay, let's see. So all these other things we're going to kind of talk about, you know, throughout the unit here. So red blood cells are the formed elements, white blood cells and platelets, that's the solid part of blood. We talked about that in lab. We looked at a blood smear in lab, so you can identify those. We're not going to spend a lot of time on that. We already did. So where did these cells come from? When I look at all these wonderful cells with unique functions, where do they come from? All cells are made in an organ, are part of an organ, I should say. And where do they come from? They come from stem cells, which are early cells that have no specific function yet, but their job is to divide and develop and differentiate to become the different cells. And what do we call those cells? Like there's labs around the US that are growing heart tissue and they're growing brain tissue. What do we call those cells? There's a lot of controversy around them. Sometimes they come from embryos left over from in vitro fertilizations that weren't used. Stem cells, yeah, stem cell research can be a little bit controversial depending on where those cells come from. We have stem cells in our skin, and we have stem cells in our bone marrow that produce these red blood cells. So all these red blood cells were produced in the bone marrow. That's where they come from. So if you have leukemia, you have white blood cells in the bone marrow that are dividing out of control, and they're non-functional, abnormal white blood cells. So people get bone pain from all those blood cells, you know, filling the bone marrow and causing pressure, and they also have lots of infections and fever because the immune system isn't working properly. If I have too many red blood cells forming, that can cause clots because these red blood cells come through our capillaries single file, those tiniest of capillaries, and if we have too many of them, they clog up. So the process of forming red blood cells in the bone marrow is called hematopoiesis. It's poiesis is how you say that, or hemopoiesis. So it occurs in the bone marrow, so they enter the blood vessels. So red blood cells are all the action is at for keeping us alive on a minute-to-minute basis. So they are biconcave and anucleate. Anucleate means no nucleus. Really, really important that you remember that. No nucleus. And because of that, they're collapsed in the middle. And what Halloween candy is collapsed in the middle and has thicker edges? What? Smarties, yeah, sweet tarts, right? So that's kind of what a red blood cell looks like. It's collapsed in the middle because there's no nucleus. And what's inside of that cell is hemoglobin, which binds carbon dioxide and oxygen There's some fat, some ATP, and some carbonic anhydrase, which we'll learn a lot about that function of that enzyme in advanced A&P. So the function of red blood cells are to transport oxygen from the lungs to the tissues and carbon dioxide from the tissues to the lungs. So it's picking up oxygen in the tissues, picking up oxygen in the lungs, dumping it to the tissues, and then it's picking up the waste product carbon dioxide from the tissues, taking it to the lungs to be exhaled away. So hemoglobin binds oxygen and carbon dioxide and gives blood its red color. So if we look at the hemoglobin molecule, what's in the center of it? Can you read that? Iron. So we need iron for functional hemoglobin to make hemoglobin. This is a protein. It's a globular protein, and it has spots for binding oxygen and spots for binding carbon dioxide. The oxygen binds to the heme portion of the hemoglobin molecule, and the globin, the brown larger structures, those bind carbon dioxide and nitric oxide, which is important for blood pressure. Nitric oxide, I don't think we don't really refer to that much even in advanced A&P. But anyway, so transporting oxygen, transporting carbon dioxide. So if a person doesn't get enough iron in their diet, if they have low iron, that's called, and it causes less hemoglobin and red blood cell function, we call that anemia. Iron deficiency anemia is the #1 cause of anemia, and it's easily corrected with an iron supplement. Ferrous gluconate is a really good iron supplement, but it can be really hard on the gut. It makes some people really constipated when they take iron supplements. So high iron foods are like raisin bran, grape nuts, dates and raisins, and green leafy vegetables are high in iron, and red meats. Liver is a really good source of iron, but we don't want to eat a lot of organ meats very often. They recommend liver like once a month. But if you like green leafy vegetables like spinach and just those really green salads, those are good sources of iron. So if we look at a red blood cell, it has 250 million hemoglobin molecules, because these are small little proteins. And there's 4 little areas for oxygen to bind on that. That's 250 million hemoglobin times 4 hemes. That's how much oxygen one red blood cell can carry. That's a lot of oxygen. So if we look at where oxygen is found, most of it is bound to hemoglobin. It's loading up the school buses, which is a red blood cell, and then within that is hemoglobin, that's the seats. Think of the seats in the school bus as hemoglobin, and the bus is the red blood cell. So most of our oxygen is on this bus. The good part of that is if breathing stops from choking or a clot stops blood flow to an organ, the bus stops and starts unloading oxygen from the seats, from the hemoglobin. That gives us a little time before the body dies from lack of oxygen, those cells. We have about, 5 minutes, depending on the activity of the body. If it's someone falls into a cold lake, they can live longer because metabolism slows and there's less demand for oxygen. And we do that in the emergency room, and in critical care we pack people on ice, induced hypothermia, to slow the metabolism down so the brain and the kidneys are not using as much oxygen, and we can prevent damage while there's that blood flow impairment going on. So that's the beauty of hemoglobin. It just holds on to oxygen, so it's a ready supply as we need it on a second-to-second basis. So if you have low iron anemia, you're going to have less oxygen, you're going to feel tired and weak, you're going to look pale. Depression is related to anemia. So you should get your iron checked when you go in for your doctor appointments, and we do check it in advanced A&P.